You know, you can always tell people about, what you want to do is, okay, we got a table like this, but what we need is some factual, you know, we need some factual data or some experimental data that tells us, fluorine's at the top of the chart here, but how reactive is fluorine? So when I started working with fluorine, they told me, well, fluorine is very dangerous, right? Okay, it's very dangerous. But you got to put it in some kind of perspective. And so what they did was they told me fluorine will catch stainless steel on fire. And then when I heard fluorine's going to catch stainless steel on fire, then I thought, no, I'm not going to try that. I'm thinking that's some dangerous stuff, right? That's a powerful oxidizer. Yeah. So you got to be careful with that. And so oxygen, look at oxygen. It's way down here. Actually, oxygen's up here too. This is one we use, O2 gas here. And so oxygen still, is oxygen a powerful oxidizer? Well, it's mid, right? It's in the middle. And then hydrogen. Hydrogen is a reducer, right? But the most powerful reducer is lithium. Lithium is very dangerous. The battery plant that burnt down. Water, water will catch lithium on fire, that kind of stuff. Hydrogen's kind of strong, mid-range, moderate, we'll say. So oxygen's a moderate oxidizer, hydrogen's a moderate reducer, right? And so if I have some hydrogen here, it's a moderate reducer, so if some leaks out of the balloon, I'm not going to worry it's going to spontaneously combust. That spontaneous combustion is called pyrophoric. There are some materials that will just spontaneously combust upon contact with air. Right? And so I just got pure hydrogen in here. And then if I were to add pure oxygen, that would make it more reactive, but I'm just going to use exhaled. I'm going to just blow into this and breathe some air into here. Exhaled air, what the percent oxygen in exhaled air is? 16%. Thanks. Versus what is the oxygen in here? 21. Okay. So a little less oxygen. More CO2. But CO2 is not going to be that, Oxygen is much more powerful oxidizer than CO2. I need, what do I need? Twice as much hydrogen as oxygen, right? It's 2 hydrogens for every oxygen. And so, you know what? Maybe that's close enough. I didn't put that much hydrogen in here. I should have put more hydrogen, maybe. And so this is just moderate. Did I do this? I probably did this in Chem 1A. I'm sure you guys have seen this. No? All right. And so right now, I've actually, I'm going to use this tape here. This tape doesn't stick very well. I'm not going to light it here. Yeah, this is what we call metastable. What does metastable mean? This is a metastable mixture because do you feel comfortable having a balloon of hydrogen and oxygen like this? I mean, if it hits the hot lamp or something, it could happen. This is metastable mixture because I don't feel comfortable either holding it like this. It's metastable, but I'm not that worried because it is pretty metastable. Metastable means what? Do you guys review like new words and that type of stuff that you encounter? Yeah. It would be what is metastable defined as? Best to review it well before the test. Not that I'm going to ask you about metastability. I'm just curious if you guys popped out on that. Where should I do this? I'm going to do it in the hood. Should I do it?
Those words. Here we go.
might be a job. I didn't put that much. So basically, this is a mid-range, oxidizer, mid-range reducer. Zach, can you hit the lights? This is great. You can cover your ears if you want to.
I remember that from the test too.
But I can't.
Yeah.
Okay, are you guys ready?
It should be a good boomer. It's going to be a boomer.
Ready? 1, 2, 3.
There you go. Yeah. Hindenburg. Yeah, she is. That was a nice impression.
Actually, that was a bit of a dud because with oxygen, with pure oxygen, it's a little more spectacular.
That was good.
What's that? Okay, yeah. So redox is a bit different, We didn't even take the most powerful, but if you take the most powerful reducer and the most powerful oxidizer, you're going to ask for a really nasty reaction. And so we're talking about pretty big energetics here, right? As far as differences in stability based on oxidation states. So anyway, that's the topic of this, and so.
I saw a big bang of fire.
So this chart method is pretty simple because all we do is inventory, find the strongest oxidizer, strongest reducer, and then we combine. But when we combine them, it's not as simple as acid-base because acid-base only 1 proton's transferred. In redox, we could have 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons transferred. Since we have different numbers of electrons, what we have to do is we have to balance the half reactions by multiplying by some coefficient, and then add them. And then we simplify it. And then we look for a driving force. When we do the driving force, we want to go from stronger oxidizer, or SOA, to weaker oxidizer, WOA, stronger reducer, SRA, to weaker reducer. And this method always yields a net ionic equation, so you don't have to do the full complete. You can, if you go backwards, work. It's not that difficult. You don't have to worry about this part. And so let's use the chart method for something like this. The reason I don't do, you would not see this reaction in Chem 4. And depending on who you took for Chem 1A, you might not see this reaction, or you might see it. Probably see it. Chem 1A, you do this reaction. But I do this in Chem 1A. I give this reaction, and people tell me it should form copper nitrate. Is it copper 1 nitrate or copper 2 nitrate that forms? What's more stable, copper 1 or copper 2? Copper 2. So it's copper 2 nitrate, it's aqueous, plus hydrogen. And they use the activity series, Hydrogen gas is more active. And so they get no reaction from it. This is correct, there's no reaction like this. But there is a redox reaction. And so what is the redox reaction? And so did you memorize a pattern when copper reacts with nitric acid? Did you memorize a pattern for that? How were you taught to figure out the products when copper reacts with nitric acid? In other words, this pattern works if the acid we're dealing with is called a mineral acid. Because in a mineral acid, this pattern fixes things. In the single replacement, A is the reducing agent, the cation is the oxidizing agent, and the anion is the spectator. Always in this pattern. This is the A plus BX pattern. But sometimes this pattern's wrong because the cation might not be the stronger oxidizer, the anion might be the stronger oxidizer. And so this pattern does not work for oxidizing acids in which the anion is a stronger oxidizer. Right? And so what you have to do is you don't memorize 2 patterns, you got to memorize a whole plethora of patterns if you want to do single replacement style. That's a waste. It's a waste because the chart method is much easier. We don't have to memorize all those. And so the reason why, but you know, a lot of people complain to me, the chart method's too hard. It's not in the book. It's not in the book, it's too hard. It's not too hard. It's not that hard. All you need, you know, is practice. You do a few of these and you're going to master it. There's the people who give up before even working through it. And so let's inventory. We got copper, solid, H+, nitrate, and water. And so this would just be like acid base. We inventory. And then we just look at the chart. You don't have to know about oxidizers or reducers. You look it up in the chart. Copper is a reducing agent. It occurs on the reducing side. H+ is an oxidizer. Nitrate's a bit tricky because it's nitrate and H+. The ratio is, it's a 4-to-1 ratio, but it's still nitrate and H+ is an oxidizer. And water is an oxidizer. And a reducer. Both. And then we just look at the chart. What's the strongest oxidizer? What's the strongest reducer? It turns out this combination of nitrate and H+ is the strongest oxidizer. And the strongest reducer is not water, it's copper. And so the reaction is going to be between these 2 species.
Why is water both an oxidizer and reducer?
It can go either way. Why? Basically, you don't have to ask why yet. All you have to do is just make sure you know it's both. So we look for water. There it is. Water is on the oxidizer side. It's H2O, gains 2 electrons to form hydrogen gas and hydroxide. If you want to know why, we can tell why. So when we look at the oxidation states, hydrogen is +1, oxygen is -2. Oxidizers want electrons. Which of these 2 atoms wants electrons, hydrogen or oxygen? If either. Hydrogen. And so if hydrogen gains electrons, what forms? Hydrogen gas. This has oxidation state of 0. So it's the hydrogen in water oxidizing. Well, is water a powerful oxidizer? Let's say I'm burning. Let's say I'm burning some old papers. You know, there's rubbish or something. That old papers. I'm burning those, and they do this with garbage. A lot of places they burn it, right? Prevent landfills or whatever. Also increase CO2. But I'm burning paper. Should I spray water on it to give it some more oxidizer? No. This is one of the worst. Is it the worst oxidizer? Yes. Is water the worst oxidizer on the chart? A lot of people, not a lot of people, some people will say it is the worst. It's at the bottom of the chart. But there's something funny about this chart. What's funny about the chart? Yeah, this is a little subset. Oh, I damaged something.
Oh man, let's all get out.
Fortunately, it was Ulysses. What we said I wasn't near that bit, right? Ulysses? No. That's no big deal. Is water really? No, water's not at the bottom of the chart.
Oh no, there comes again.
Is one of those like good subject? Is that always set off the run in the other one?
Did you put smoke in here?
Yeah, it's probably the one in the back.
Yeah.
Where you're using. Another individual.
They're doing some work on this. Let's screw it up. Unfortunately, we hear that all the time in Chem 1B. Because Chem 1B, we work in the hoods a lot, and so if you hear that, it's just when the flow of the hood goes below a certain point, too many hoods are open, or somebody goes in and out of the room, it upsets the air flow. And so it's nothing to worry about. If you hear all of them go off, then that means all the hoods are dead. And so don't do anything that generates H2S or HCN. We used to have cyanide, but like the CDC, we decided to get rid of it. It's too hard to control. Some people don't listen. We still have sulfide. And so no matter how many times I tell people, do not add acid to sulfide on the lab bench, you still do that. We have to evacuate the lab, stinks up the whole lab, everybody gets a rotten egg headache. But I've slowly phased out the sulfides. I used to work with sulfides a lot. I think I mentioned that earlier. And so I'm glad to get rid of them. But,
Rotten egg.
yeah, every day I work in a research lab with lots of sulfides, and every day you go home and you just bring the smell with you. All your clothes smell like sulfide, everything. Even if you wear a lab coat, you know, everything smells like sulfide. Sulfur. Look it up, thiols. Anyway, this chart's very odd. And so what we have to do with this chart is we have to use these numbers. We aren't going to deal with these numbers until later, but you're going to use these numbers to position them in the chart and rank them. And so if you look at water, water has a minus 0.828 volts. This is actually volts. And so which positions water between zinc 2+ and aluminum. And so the way I read this is that water is a stronger oxidizer than zinc 2+, but a weaker oxidizer than aluminum 3+. That's where we. So in other words, water is a pretty weak oxidizer. Water also occurs on the other side of the chart many times. Look at water, 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 water. Sometimes it occurs with something else. Sometimes it occurs by itself. This is where, how about you Chem 1A people? What's the pattern here? What's the pattern with water? I'm asking it backwards. Because in Chem 1A I asked you, what's the pattern with the H+. You guys remember that? What was the pattern with the H+. So for example, I said nitrate with H+. This combination is a better oxidizer, the combination. But when you look at this chart, take a look at this chart. H+, 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 H+. You guys remember the pattern? No. It's okay. Well, there's a pattern. We'll just ignore it for right now. But we're going to go down here, and so which water should we choose? We could choose this water. But if this water loses electrons, now what in water would lose electrons? The oxygen would. If this water loses electrons, look at the product. We go backwards here. We form hydrogen peroxide. That makes sense because in water it's -2, and hydrogen peroxide, oxygen is -1, so it's lost 1 electron each oxygen. There. Well, hydrogen peroxide is not a very stable product. Look at this water here. This water loses electrons to form O2. So it goes from oxidation state of -2 to 0. And so O2, that's a more stable product. And so that means this water is a more powerful reducer than this, which makes sense. This water is closer to lithium. And so we look at this water here. The water is not the greatest oxidizer or reducer, but we have to You know, the people that say, why do we need water, are probably the people who sprayed water on the lithium fire. You know, because we don't need water because 99.9% of the time I don't have to worry about it. Unfortunately, when they had that fire, that was the 0.1% of the time that they should have worried about it. Well, anyway, so all we do is look. We look for our strongest oxidizer present. Going down. The first one we hit is nitrate and H+. 1 nitrate, 4 H+. Don't worry about the ratio here. The ratio comes after we balance it anyway. And so we need nitrate ions and acids, other than nitric acid. That takes electrons to form nitric oxide gas. We continue down here. Here's H+. H+ is considerably weaker than nitrate and H+. All acids have H+ in common. But oxidizing acids will have something else.
How about sulfuric acid?
Sulfuric acid, we would look for sulfate here. Here it is. This is sulfuric acid. It's sulfate with
Hydrogen.
H+. We would need 2H2SO4. One of the sulfates would be spectator, the other sulfate would react. The same thing here. If we had nitric acid, we'd need 4HNO3s. 3 of the nitrates are spectators, 1 reacts. That's it. So sulfuric acid is considered a oxidizing acid, not a mineral acid. But look how much, is it much more powerful than just a regular normal mineral acid? Well, not that big a difference. Wait a minute, I have copper 2. Do I have copper 2 present in this mixture? Do I have copper 2 present? Not yet. I have no copper 2 present. I have copper metal. Copper metal is not an oxide. Copper metal is a reducer. Some people, I don't know why, they don't pay attention to the chart. And so some people will say, if I mix copper metal and nitric, they'll have copper 2. And I'm thinking, where did you get the copper 2 as a reactant? You know, as a product, no problem, but as a reactant, I don't know. And so basically the strongest oxidizer we have is nitrate and H+. Now what's the strongest reducer? Well, we had 2. We had water and we had copper metal. Here's copper metal. Where was water? Here's water. So the stronger reducer will be the one closer to lithium, that's copper metal. Okay, does that make sense? See, here we don't need to know why. Here we just need to read the chart. That's all. Later on, you ask yourself why. But first, you just get the method down so you don't get hung up. All right. So what I do here is I just use the chart. I copy those reactions, those equations in the chart are called half reactions. And so I just copy the half reactions off the chart. And so when copper reacts as a reducing agent, the half reaction is this. Cu solid goes to Cu2 plus 2 electrons. What I did was I took the reaction off the chart and just reversed it. Because I don't have copper 2, I have copper metal, so I'll just go backwards. But I don't want to write it backwards, I got to write it forwards because copper is my reactant. And the other reaction is 4H plus nitrate plus 3 electrons yields NO gas plus 2H2O liquid. And then I got to add these up. But the problem with adding these up is this. Copper produces 2 electrons. Nitric acid consumes 3 electrons. It's mismatched. To fix this mismatch, I'm going to multiply the top one by 3. And so I produce 6 electrons. 3 coppers will produce 6 electrons. And I'm going to multiply the bottom one by 2. So I consume 6 electrons. Then that works. And so now I'm producing 6 electrons, consuming 6 electrons, and I get this. 3 copper solids plus 8 H plus 2 nitrates plus 6 electrons yields 3 Cu2 plus 6 electrons plus 2 NO gas plus 4 H2O liquids. Okay, this. Now I'm going to simplify, but before I simplify, I want to see if there's a driving force. What is the driving force? Is this a useful review for you guys?
Yeah.
The driving force is going from a stronger oxidizer and stronger reducer to weaker. The easiest is by using the conjugate relationship. What we do here is, this is the reducer. Therefore, its conjugate must be the oxidizer, which makes sense. Going backwards, copper 2 takes electrons. This is the reducer, H plus and nitrate. Oh, sorry, not reducer. This is the oxidizer. Therefore, its conjugate, NO and H2O, must be the reducer. As going backwards, NO and H2O produce electrons. So that's the easiest place to sign this. And so then we compare. This is the reducing agent here. This is the oxidizing agent, these two. This is the oxidizing agent here. These two are the reducing agent here. And then we go to the chart, nitric acid versus copper 2. Nitric acid versus copper 2. Which is stronger? And so I have nitric acid here. I have copper 2 here. So it looks like nitric acid is stronger. Okay. Then I have, for the reducers, copper versus NO and H2O. So the reducers are copper versus NO and H2O. Copper is a more powerful reducer. This is lithium. Because of the conjugate relationship, it's always got to be strong, strong, or weak, weak, or weak, weak, strong, strong. And so now I'm going from stronger, stronger, to weaker, weaker, and I got driving force. So the reaction should occur here. And so for single replacement, we got no reaction, but for the chart method, we did get a reaction. Now, we can simplify this because these electrons, cancel, 6 electrons, 6 electrons. The waters, so the waters don't cancel. Actually, that's all we can simplify. And so after we simplify it, our net reaction is going to look like this. It's going to be 3 copper solids plus 8 H plus 2 nitrate yields 3 Cu2 plus 2 NO gas plus 4 H2O. This is our net, and the driving force is I connect these because we need these together. It's not just nitrate, but it's nitrate with the H plus. The H plus is important there in the reactivity. This is it. Now, when you can dissolve copper in nitric acid. You can't dissolve copper in hydrochloric acid, let's say. But when you take this, there could be subsequent reactions with products. So for example, NO is a colorless gas. But usually when you do this reaction, you produce a brown gas. So what happens is in step 2, the NO gas gets oxidized by oxygen and air to produce NO2. NO2 is a brown gas. It looks like smog. It was part of photochemical smog. And so this would be the next reaction that occurs. And so somebody asked me, you know, with spectators, do you ignore them? Yeah, spectators you typically ignore, but sometimes the spectators will actually react in a step 2 with the products that you just formed. That's happened. And so if you're sharp, you can catch those occurrences because you know, oh, that was a spectator in this case, but now that I formed this, oh, I see those two ions like each other. I'm going to precipitate. That kind of thing. All right. For the homework, these methods are basically what you need in addition to one more, the skeleton redox. And so let me just briefly show you. Potential diagrams is beyond the scope, I think, what we're going to do. We're not really going to do much with potential diagrams. Potential diagrams is to figure out more trickier here. The skeleton redox is we do this. We separate it into half reactions, and then we balance all elements other than H and O. We balance the O's by adding water. We balance the H's by adding H+. We balance the electrons by balance the charge by adding electrons. We double check. We combine the half reactions, etc. And so you get 2 types of questions in your homework. One, where you have to figure out what the products are. Or 2, they give you the key products. When they give you the key products, the skeleton redox, and you know that, you know, those are the main products that form in this particular reaction. When we deal with potential diagrams, we see, you know, ethanol can be incompletely combusted. You know, have you ever heard of wine turns to vinegar? Yeah. Wine turns to vinegar is incomplete oxidation. Because what happens when wine turns into vinegar, it's partially oxidized. The ethanol in wine is partially oxidized to acetic acid. Well, this is a partial oxidation, but rather than forming acetic acid, this is in basic conditions, so we form acetate. And so it depends, you know, it depends on how vigorous the reaction is. We can combust ethanol all the way to CO2 with permanganate. In fact, you do that in Chem 1A. You guys remember the permanganate with, was it with the ethanol? No, it was with chlorine. It was with chloride. Yeah. Well, anyway, you could do this all the way to CO2, but it's not going. We're not going to go that vigorous. So work on those homeworks, and then if you have questions. I got behind, so I'm already behind schedule. I was supposed to finish chapter 24, parts 1 through 3, but that's okay. It was fairly short. The reactions are important because we're going to have a test. We're still going to have a test on next week on Thursday. It's the plan. What's that? Are these, some of it is in the book, yeah.
What chapter though?
Chapter 5 and chapter 20.